This is Professor Coles. I'm going to give just a short segment on propellers to prepare us for the propulsion part of the class. As I mentioned prior, that there's some confusing elements of this, and so it's important to get the basic concept down before we get into the details. Just some nomenclature. We're going to be working fundamentally with marine propellers, but this does apply to all propellers. So looking from astern, you might have a three-bladed propeller. It looks like this. Hopefully it doesn't look like that, but if it happened to, well, you deal with it. The diameter of the propeller, we have D, the diameter, which is the diameter of a circle, which encompasses the tips of the propeller blades. Then you have the hub, this thing here. The hub tends to be quite thick relative to D because of structural constraints. So each of these is a blade. The rotation rate of this can be designated a couple of different ways. One is RPM, rotations per minute, which is usually capital N. You have rotations per second, RPS, which is a little n. And then you have your usual angular rotation rate, omega, which is in, so this is units of rotations per minute, RP, R over M, and is rotations per second, and omega is units of radians per second, and therefore omega equals 2 pi n. So you see all three used. Just be careful, particularly between capital N and little n, that they are quite different. So those are the key ones for there. We'll also look at pitch, which is an extremely important one. So if I take, let's see, best way to explain this. This is a propeller looking from astern. Let's say it's rotating counterclockwise. We're looking from aft of the boat, and it's gone by us, rotating counterclockwise. Now we have a different aspect of looking at it. We have, let's say the boat hull bottom is here, and we put a viewing port right here, looking right down over the propeller. So you're seeing with your eye straight down on the propeller like this. So looking down, it might look something like this. So again, this is from inside the boat, looking straight down on the propeller. Looking at the propeller like this, so the shaft might be underneath it, somewhere around there. There's the hub here. And so it's rotating, and this blade at this instant is moving to the left as you look down based on our counterclockwise designation. So what pitch is during a rotation, essentially you unwind the helix. So let's say what we've done is slice the blade right here, and this is a little bit of blade element theory. So I slice the blade along a radius. Let me make sure that this is clear, that this is along a radius. An upper radius and a radius that's a tiny bit closer to the hub here. So the thickness between those is a DR, a differential thickness. So this is just this element represents the blade along this slice in here, in this little red region here. Is designated here. Now over the course of one travel, this blade will move linearly. If we unwind the helix, it will remove linearly a distance 2 pi times r, where r is the radius of that section from the hub. At the same time, if we assume for a second that the propeller is driving just as a screw would when you put a screw into a wall, assume the propeller is driving through a solid substance, say wax or something like this. So it will climb its way around and move a distance equal to p. That p is the pitch. That p is the pitch. How far it climbs as it moves through this sort of a waxy substance during one rotation of the propeller. So if the propeller is at 0 angle of attack, if we look down at the propeller blade, and they all looked like this, all the sections looked exactly like this, symmetric section at 0 angle of attack. Now this propeller would not be a very good propeller, as you can already see. It's just going to spin in space. It won't move at all through this imaginary wax, and so the pitch of that is 0. So you can see this geometric pitch. We're talking about geometric pitch is related to the angle of attack, and just like it is in a screw, it's the threads per inch. So here it's the angle of attack, and if we were to change the propeller to higher angle of attack and twist it one rotation, it will twist even further. So that pitch is related to angle of attack. Now I'll show you in a second that these blades are generally twisted so that their geometric pitch varies with the span, and there's a reason for that, which we'll see in a second. So when we talk about propeller pitch, they're usually discussing pitch in the context of there's different ways of doing it, but they're usually doing it in the context of the 70% radius. So you're considering what's the pitch here. It's 70% from the hub out to the tip. That's the pitch. So that's geometric pitch. It's just related to the angle of attack and the radius from the hub. Propellers are pretty funny beasts. I'll give some links for the basic idea of momentum theory and talk about it a little bit in class. The basic idea, if we look aside from the propeller, from the side, so here's a drive shaft. Essentially the fluid has to be accelerated across this pressure disk. So there's a pressure jump and there's a momentum jump across this propeller blade. And so if we look at streamlines, they'll look something like this. So this is forward of the propeller, and this is aft of the propeller. Now momentum theory will show you that the acceleration of the fluid doesn't occur just after the propeller. In fact, it occurs before the propeller. So somewhere just in front of the propeller we define a velocity VA, which is the advance velocity. So the fluid's already been accelerated from a free stream velocity very far from the propeller here, which would be the ship speed, to this VA. Now there are other factors affecting VA beyond the acceleration purely due to the propeller acting on the fluid. The second factor are wake effects. Because the propeller operates in the wake of the ship, the fluid regime there is very different than it is in the free stream flow aside the ship. It's in the boundary layer, possibly separation zone of the ship. The stern wave can be present there, so you have wave-induced velocities, and all these affect the velocity felt by the propeller. And they all go into this VA. So it's a fairly complex calculation. We're going to look at VA from 2 points of view. One is an open water point of view, where essentially we have the propulsion working on its own with no ship at all and no free stream perturbations. That's how they're tested. Then we're going to add in the effects of having the ship there, and they aren't necessarily detrimental effects. Sometimes flowing down the fluid is beneficial to the efficiency of the propeller. So we will look at these wake effects and the difficulties they impose in a later lecture. So this VA again is the advance velocity of the propeller. Again, it's affected by these two factors. One is represents an acceleration of the free stream flow due to the propulsion working, and also the wake effects of the ships. VA is this advance velocity. Now, if we look at a section of the propeller again, so we're going to go back to our picture here for a second. Excuse my scrolling. Here, again, we're looking down through this port at this red slice. So we somehow cut off the propeller outside of that. And we're looking magically at this red slice as it rotates around. Looking from stern, again, we're assuming counterclockwise. So we're looking from above. and we have our blade, and it looks something like this. And so generally propeller sections look like little airfoils, typically more near the hub, where cavitation's less of a concern. As you get out towards the tip and cavitation is more present, or more of a concern, then they start to morph into beasts that are basically designed to avoid or control cavitation. They're much thinner, and sometimes they sort of have a flat bottom and a hemispherical top. They look very different than what we consider an airfoil, but for the sake of argument, we're just going to look at it from the point of view of an airfoil, because these are lifting devices, and I really want to make sure that that's understood. So this device is moving from right to left from our point of view. It's rotating in the fluid, and we have the whole propulsion is moving, or there's a fluid moving into the propulsion at VA. We're going to look at it at this instant from the point of view of this little slice of propeller. Just at this instant, what are the fluid velocities as seen from the point of view of this propeller? Well, there's one, well actually let me start off with defining. Here's the propeller plane in this direction. That's the propeller plane, the plane of rotation of that propeller. Again, the axis of the rotation is along this dotted line, and the pitch angle of that propeller is this geometric property. We'll call it phi. That's the pitch angle of that little slice of propeller outside of the propeller plane. Now, what are the velocities experienced by this propeller? We'll make them red. It's feeling a velocity in this direction, and it's feeling it's feeling a velocity, the advanced velocity, I did put it here. So we have this velocity, this is circumferential velocity, we'll call it 2 pi nr. So coming back here, what is the velocity, the circumferential velocity at any point of the blade? It's equal to omega r, which is equal to 2 pi nr. That's just the velocity. The circumferential velocity is a function of radius for a solid, a body in solid rotation, omega r, which I wrote as 2 pi nr. So it depends on the rotation rate n, and depends on the distance from the hub. Both of those, as both of those increase, this circumferential velocity is going to increase. Now in reality, there's another effect here, because as the propeller spins, it kind of starts to get the fluid moving circumferentially due to the drag. So the water, it tends to pull the water in the direction of the blade. So when the next blade comes around, the water's already sort of started circumferentially, so it's not experiencing this full velocity. But we're going to ignore that for now. Just think in terms of kinematics. We have the 2 pi nr, or omega r, coming at it, and then we have, and I gotta draw this right, or else it doesn't work out. And then we have a advanced velocity here, VA, coming at it from this direction. So again, we're looking down at the propeller from the ship, and the bow of the ship is here, and the stern of the ship is just after the propeller, say it's right here. So VA is this advanced velocity, which, as I mentioned, takes into account a lot of different factors. But you can think of it kind of like the ship speed, something like the ship speed. Now the propeller doesn't know anything about these two separate components. It just feels one local component. And so I will do the resultant component. I'll make it green. It's something like this. However, that is fairly poorly drawn, so let me get this right. The green component, which is going to be like this. That's the resultant component of the velocity aimed at the propeller. So the propeller still has some angle of attack. You can see relative to that green line, it has some alpha, which I'll designate in green, alpha. That's the fluid mechanical angle of attack that we've been talking about in terms of airfoils over at least the middle of the semester. So being an airfoil at an angle of attack, it will produce some lift. Let me erase this VA. Give me some room. It'll produce some lift. Now, lift is normal to the free stream direction. By free stream, I mean the local fluid velocity, the green line vector direction. You will get a lift. You will get a drag. Drag is parallel to the local free stream direction. A lift and a drag. Now, the two things that we are concerned about, and these lift and drag directions are going to vary depending upon the angle of attack, the rate of rotation, everything else. What we want to do is decompose this into two directions that are useful and important to us. And those are, and I'll designate those in purple, parallel to the ship travel, and we'll think about a thrust. A force parallel to the ship travel is thrust. It's the useful force of the propulsion to drive the ship against the resistance. And then we have a force in the propeller plane, which is going to be a torque. So I'm going to call it here Q. I don't want T to be torque because I already have T to be thrust. So Q is going to be our torque. And that's essentially a force in that direction times the radius, times the distance of this little propeller section from the hub. Gives us a torque. So T is good, that's thrust. We want that. Q is bad. Q is what your horsepower is fighting against. It's resisting rotation. It doesn't want to rotate because of the Q that's acting on it. So if Q is positive, and will be, it's resisting rotation. That's what the horsepower is fighting against, Q. We want a lot of T with not much Q. If we have that, then we have a very efficient propulsor, provided we're actually moving forward. So these vectors aren't necessarily drawn to scale, but those are the two important forces. Here you see in this particular configuration that the lifting force of this little section has some T and some Q if you were to decompose that. So lifting force is providing our thrust, but it's also adding to Q. It's adding to the necessary horsepower. And the drag force in this particular setup here actually works against the thrust. It's negative thrust direction if you decompose it in the up and down coordinate on the screen, and then it is acting in the direction of the torque. Basically, the drag on this element is working directly against the engine. So that's the scenario. So think of the propellers made up of these many, an infinite number of these little tiny airfoils. They're spinning around. They're seeing a local fluid velocity that depends on two factors: their rotation rate and distance from the hub, that's one factor, or 2 pi n, I missed a factor there, sorry, 2 pi n r, and you have the advance velocity, VA. And those two come together to give you a resultant fluid velocity, the green fluid velocity, and that's ultimately what's felt by the foil as it spins around and generates lift and drag, which can be decomposed into a T and a Q. Now there's a couple things we can look at. First we're going to do is keep everything the same, and we're just going to consider this airfoil, this foil, to be closer to the tip at a larger R. So everything's the same. It's rotating the same velocity, same advance speed. The only thing is we're slicing our propeller further out towards the tip. So R is bigger. Now what happens when R is bigger is that this fluid velocity here, this fluid velocity here becomes bigger because R is increased, and therefore the resultant fluid velocity, I'll make a green line, tends to come down a little bit, closer to that fluid velocity, closer to the propeller plane, and therefore the angle of attack increases. The angle of attack has increased simply by rotating this thing faster. So the propeller's not rotating faster. This little section's going faster because it's further from the hub. So it has to cover a larger distance in the same time, and therefore it's the velocity and the circumferential velocity, the velocity in the propeller plane, is increased. But VA is the same. But it's those two together that make the resultant vector, and therefore our angle of attack has increased. So if we were to keep the same pitch angle all the way down the propeller, then the sections at the tip would be at a much higher angle of attack than they would be towards the hub. So that's a very important concept. So what you do is you twist the propeller. Generally these sections are twisted for that reason, because the alpha will naturally increase towards the tip because the velocity, circumferential velocity, is higher at the tip. So it's experiencing more of that than the advanced velocity. And therefore you twist them in. So essentially an airfoil at the tip if this is the airfoil at the midsection, the airfoil at the tip will be twisted down. We'll make it a funny color, we'll make it brown. So it might look something more like this at a lower angle of attack. If you drive or you go to Fairhaven, you go to any of these places and look at a wind turbine, it's no different. The wind turbine blades are twisted. And so that's a good example of one if you live in that area on a light wind day or a zero wind day. The turbines aren't spinning. You can walk, we have one on campus. So you walk directly under the one on UMass Dartmouth campus. You will see that the blades are twisted so that geometrically, so that the angle of attack, or the pitch angle, the geometric angle of attack, is smaller at the tips than it is the root. It's a very complex process, and propellers is even more complex, I'll venture to say, because you have to deal with cavitation and deal with circumferential loading, which we'll talk about, wake effects, which drive you to deal with vibration problems, severe vibration problems. So it's a very complex thing to design these things. And you have severe structural constraints because you're dealing with a high density fluid. So the loading on these little blades can be severe, and that's why, as I mentioned before, when you look at a wind turbine, the hub is a little tiny thing and the blades are really skinny near that hub, but you cannot do that with marine blades. It would break right off. So so you tend to have a thicker hub, and then you're not loading the blades near the hub. So that's an important effect. What you can also see here, let me just clean this up. Let me go back to where we were with VA and VN. I don't know if, oh, wow, look at that. You can do that. So back to our original mid-section foil. Now what happens if you were to run at a smaller VA? Basically kind of like slowing the ship down. As we make VA smaller, so we have our initial free stream direction, looks something like this, giving us our alpha here. And now we're going to make a smaller VA. So let me try to erase a little bit of VA. So make VA smaller. It does the same thing. It brings our resultant vector down so that our resultant airfoil is now at a bigger angle of attack. So going slower, keeping the RPM the same, does the same as moving outboard. So this one midsection, so we're staying at the same section, we're just changing the flow conditions, we're slowing the ship down. Now this same section's at a higher angle of attack. And as you move towards a case of VA equals 0, which is known as the bollard pull condition, you can think of this like as the instant you turn on a tugboat, so you're tied to the dock. And so you're bringing your advanced velocity to 0. How much thrust is it generating? In that extreme case, VA is 0. Let me erase all this stuff here. VA is 0, and the propeller is still turning. So it's feeling only one velocity component, which is the circumferential velocity component, because VA is 0. And so it's at the maximum possible angle of attack. And in that condition, the thrust is the largest. T is max. Let me say this. T, or thrust, is max in general when VA equals 0. So this is provided we have a decently designed propeller that isn't horribly separating from too high an angle of attack, which is certainly possible. So a well set up propeller is going to produce max thrust of V equals 0. But this large angle of attack means large lift, large induced drag, a larger viscous pressure drag, and also you will also have the max torque occurring, generally speaking, when this advanced velocity equals 0. So these are sort of some important things. So thrust is good, torque is bad, so it still leaves the question up, is this, are we at maximum efficiency when we're at VA equals 0 or not? And we'll look at that in a second. So so far we've been talking about dimensional variables. Now, just like with the ship, it's more important to think about non-dimensional variables, particularly because you want to test these. when you test these in what's called a cavitation tunnel, certainly you can't make a tunnel large enough to hold an enormous ship propeller, which might have a 5-meter diameter, in these tunnels. So you have to say, we're back to scale modeling. How do we model a scale propeller, keep all the conditions the same, et cetera, et cetera? And so the two important characteristics, again, are thrust and torque. And we're going to non-dimensionalize those. We're going to call the non-dimensional thrust KT, the thrust coefficient, and that's going to be torque over rho n squared d fourth. Let me make sure that that's right. Yes. And we have, so there's different ways to do it. You don't, you could use omega, have some pi factors in there. Is D the right characteristic length scale? Yes, we see that for most of these calculations. So this is traditionally how it's done, but there isn't, doesn't have to be this way. The torque is similar. So you have Q, the actual torque coefficient is Q over rho n squared d fifth. Let me just make sure that's correct. There's no funny factors in there. That is correct. Now, these, just like our ship drag is a function of a bunch of non-dimensional parameters, Froude and Reynolds and others which we've been ignoring, these coefficients can also be thought of as a bunch of fundamental parameters. You can use Buckingham pi theorem to get to this. And you can see that these are basically a function of three important parameters. One is a kind of Reynolds number. For example, we'll just make it a velocity scale, so omega d, a length scale d, and a kinematic viscosity nu. So this is a kind of Reynolds number. It's not necessarily a Reynolds number you'd use for a propeller, but it's a Reynolds number. Then you have cavitation, which we will talk about later. So you can write a cavitation number like how we've been doing in class. And then you have a third component, which is a ratio of velocity scales. So here we're going to use VA over ND. So ND is a proxy for the circumferential velocity. At the tip, the circumferential velocity is equal to 2 pi ND. So we're ignoring this 2 pi effect to become a cleaner. You could define this denominator as 2 pi ND if you wanted to, but you don't, by tradition it's done this way and it doesn't really matter. It's the key thing. This is a fundamental ratio. And again, this ratio is a proxy for the ratio of these two components, which I've now erased, of these two components here, our VA component and our circumferential component. That ratio of those two is wound up in this ratio here, and this is known as the J, which is the advance ratio, VA over ND, the advance ratio. As this goes to 0, as VA goes to 0, this goes to 0, the advance ratio goes to 0. So we're going to ignore Reynolds effects and cavitation effects for now, and we're going to write KT as a function of J, and KQ as a separate function of J. And we'll think about a performance curve. Now, a performance curve, generally what's done is open water tests, although you can do in-water tests as well. An open water test will go something like this. They'll have a water tunnel. Inside the water tunnel is a nice drawing in your book. They'll set up the propeller like this, the scale propeller. For some reason this is not refreshing. Hang on a second here. There you go. The water will be moving this way. So the propeller has felt nothing but uniform flow, and they can control in this tank they can actually pressurize the tank to set the right cavitation number. They can control the RPM and control the flow speed, and that allows you to control J. So you can get the same J, you can get the same cavitation number, same pressure. Now Reynolds is a little trickier, but so you try to keep these things large and spinning fast enough so that you're still in this high Reynolds number kind of environment. to reduce the Reynolds effects. And what they'll do, they'll put this in there, keep the flow speed constant, so VA will be fixed, and your pressures will be fixed, and then you're just varying N, the RPM. And again, since J is VA over ND, you will be changing, you'll be varying J by varying the denominator. That's the easiest thing to do. I don't know that that's always done, but that's generally done. With a thrust bearing, you can measure thrust, torque, and then convert these. If you know N and you know VA and you know D of your propeller, you can convert these into KT and KQ, and you can plot them versus J for this propeller. And presumably, if you've kept the cavitation effects similar and the Reynolds number up nice and high, these will be the same performance curve for the real propeller. So in the tank, in your test tank, or in your cavitation tank, it might be, it's a half meter or smaller propeller. The real propeller is 5 meters. But again, this is model testing, and we keep the right dependency on the fundamental non-dimensional numbers, and we can scale it up. KT and KQ are this on the model, they'll be this on the scale propeller, they'll be this on the full scale propeller, provided we've done things correctly. So there's a nice sketch in your book, but I'll sketch it here just because I want to relate it to what we talked about earlier. Here's J, here's KT and KQ plotted on the same curve. Now, as we mentioned before, when the advance velocity, again, so this is VA over ND, when VA is 0, J is 0, and VA is 0, we're at maximum angle of attack, and therefore a maximum KT and maximum KQ. Now, at some speed, let me just redraw our airfoil again here. Here's our airfoil. There'll be some magical speed, at which you have your circumferential velocity, you have your advance velocity, and at some point the fluid velocity, the resultant fluid velocity, will be exactly aligned with this blade, such that lift is going to be 0. Essentially, you're setting lift to 0 because VA gets to some speed. If we get VA to this speed, the propeller is producing no lift, therefore it's producing no thrust. And that's what's known as the effective pitch ratio. So somewhere thrust goes to 0, somewhere in here. And generally, I should have made that green. And generally between max and min, it's sort of monotonically decreasing. Apologize for completely destroying this drawing. So it might do something like this. Now KQ will do something similar, but in the same condition here. So again, we have here 2 pi n r on this little section here. At this point, the propeller is not producing any lift. It's not producing any thrust. However, there's always skin friction drag. So there will still be drag on that section, and therefore a torque. So even if you made a propeller, a very badly made propeller like this, symmetric section at 0 angle of attack, and you were to spin it, so you might use this to stir a tank or something, and you were to spin it, it would never produce thrust. However, it would still produce drag because you have skin friction and viscous pressure drag. So lift is 0, but drag's not 0. Or maybe it's a little bit more complicated than that, but let's just pretend it's as simple as lift is 0. So at some point in this section, thrust is going to go to 0. That's a little more accurate. Thrust is going to go to 0, but Q, the torque, will not be 0. There'll still be torque on this thing. So Q will not go to 0 at this same magic point here. Q will still be positive. So we'll make Q red, something like this. Now, this is generally plotting 10 kQ. The units work out the way it's non-dimensionalized, and the typical forces, if you want to plot them in the same chart, you plot 10 times kQ and you plot KT, and they end up pretty close to each other, so you can put them in the same graph. It's just a matter of convenience. Just be careful of that. This down here is, again, the bollard Bollard pull condition, where the advanced velocity is 0. Think of that as like a tugboat. Now, what about efficiency? Well, it's not as simple as KQ over KT. If you don't mind, I'm going to wipe this out. KT over KT. What we care about in terms of efficiency is power out over power in. How much power are we getting out? Power out is thrust, the force, times the velocity, VA. Power in is torque times angular velocity. Omega, I'll use 2 pi, 2 pi n Q. This is power out, how much power you're getting out. Thrust is good, but you got to be moving, right? So you can lean against a wall, but you're not doing any real useful work, but you get tired. You're not doing any useful work because the wall's not moving. So to do useful work, useful power, you need velocity here. So torque times VA divided by input power. So shaft speed times shaft torque is input power. So you want to have a big numerator and a small denominator. And then we'll make this eta, our efficiency. So what does this look like? So it's torque times VA over 2 pi NQ, or you can think of this as torque VA over omega Q. It's the same thing. So at low VA, apologize for something. So this is still in dimensional units, so we can rewrite this into non-dimensional units. And we're going to refer this as eta naught. We're going to see a lot of etas in the class coming up. Eta naught for open water, meaning we're ignoring wake effects, in particular the wake effects of the boat, transmission losses, things like that we're ignoring. This is the open water efficiency of the propeller as measured in a tank without any interference of the stuff. Now, if we convert these things into KT and KQ, it looks like this. JKT, I think there's a, there must be a 2 pi KQ. So it kind of looks like the same thing. But this is non-dimensional, up and down. So it's either way it's non-dimensional in total, but here we're using our KT and KQ and J. So when J is 0, eta is going to be 0 at some point. And we know at some point KT goes to 0 when we hit that, what we call that, the effective pitch speed. So at some point the thing's spinning, or you're moving forward fast enough that the propeller's not producing a thrust force anymore for a given pitch. And so it's going to go to 0. So we have either J going to 0, or as we increase J, eventually KT goes to 0 without KQ going to 0. So that implies already that there's going to be some kind of maximum occurring. So here we are, the efficiency is 0 by definition because there's no velocity. And here the efficiency is 0 because it's not producing any thrust. In between, you have thrust. Both of the numerator and denominator are non-zero, so we're going to have some ratio. So, and typically it's going to look like this. Let's make it another color. Comes up and back down. So there's going to be some speed advance ratio, which you have maximum efficiency, between two zeros of efficiency. And later on when we go to size propellers, we're going to essentially look for that point. That's the price point. That's the point at which you want to set up your propeller, roughly speaking, in order to get the lowest amount of horsepower for the most amount of torque. You're hoping for that. So we'll look at that in more detail when we go to propeller selection. So that's what I wanted to say. I think it's very important that you understand the nature, this being a rotating, lifting body, so make things a little weird, and that the flow conditions experienced in the spanwise direction are not the same. In an airplane wing, from the root to the tip, they're essentially experiencing the same streamwise direction. There's some variation due to the downwash, but the major component, the streamwise component, is not varying much. On the propeller, it's varying hugely from near 0 at the hub to much larger at the tip, the circumferential velocity. That means that to maintain the same sort of effective angle of attack, even ignoring the downwash, which you do have in propellers, you have to twist the blades. These blades are going to be twisted, and if you look closely at any wind turbine blade, any rotational machinery, an airplane blade might be the easiest to think about, a propeller on a small Cessna, it's twisted. It's simply twisted to maintain more or less the same angle of attack while it's running from beginning to end. So that's a complication versus what we were looking at in finite span aircraft before. Again, the goal is to produce thrust. So this thing is a lifting body, it's produced with thrust. Thrust is in the direction of the boat's travel, and what you're working against is torque. It's a force in the propeller plane times the distance from the hub is a torque if you integrate over the blade, and that's what the engine has to produce, is that torque to turn that propeller. Those things, thrust and torque, vary with advance ratio. The advance ratio essentially sets up the angle of attack of the blade elements. So it varies from 0, the thrust will be 0 at 0 speed. Thrust will be maximum at 0 speed, and the torque will be maximum, and the thrust will eventually reach 0. There is some point when you're spinning the prop and moving forward fast enough that the elements themselves are no longer producing a net thrust on the propeller. And the most important thing is this ratio of these two, essentially this ratio of power out to power in, which is J KT over 2 pi KQ, which is your efficiency. So efficiency will be 0 because you produce no useful power when you're not moving. Essentially, VA goes to 0. It'll be 0 once your thrust goes to 0 because the propeller's not doing any useful thrusting, even though you're working hard to turn it. In between, you reach some kind of maximum efficiency, which is the blue line you see here. So this sort of sets up our discussion. We'll sort of review this a bit in class. Then we'll be talking about what happens when you put this thing behind an actual ship in the wake of the ship, and that sort of messes with us a little bit. But we won't change this. This is the open water efficiency. This is the basics how the propeller works. We're going to keep this. We're going to essentially pull in a new factor. We're going to multiply by a factor to account for these wake effects. And then what we're going to do is work on sizing a propeller. Here's a ship. It has a certain resistance. How do we determine the right propulsion to push that thing along? Horsepower, propeller, etc.